Good morning, guys. I hope you had a very fun 4th of July. You guys stayed safe, did everything you're supposed to, and stayed out of trouble. Um, Today's our last day of material that we'll have a homework assignment for. I will be posting 2 more videos with assignments attached to them, but they're optional. If you choose to do them, you will get the points for them, so they can boost your grade. If you choose not to, you won't get the points for them, and they will not be held against you, so you'll be exempted. We'll post the post test and today's material. Material will be posted at noon like normal. The post test will be posted this afternoon sometime. All material for the class, and especially this week, is due by Friday at noon. Not Friday, sorry, scratch that. Ooh, bad. Thursday at noon. I will make sure that is in Blackboard in big bold letters. Thursday at noon, everything is due, because grades are due the following day, and I need time to grade things. So, Thursday at noon, today's assignment and the post test will be due, as well as any of the other 2 parts that you may choose to do. We'll have no assignment on Thursday, obviously, because it'll be the day that everything's due, and so we have essentially 3 days left in this class. Today's material is the last day that will be actually covered and is actually on your post test, so we'll make sure to get to that, and let's go ahead and get started. Okay. It's important to note that for today we're going to be dealing with complex numbers. Now, a complex number, also known as an imaginary number, is a mathematical concept designed to expand upon a system that we know gives us solutions. So we're going to have a short discussion today, just 5 minutes or so, discussing kind of where the concept of a complex number came from, because it can feel sort of made up. I mean, they're called imaginary numbers. How are they not made up? It's important to note, though, that anytime you talk about mathematics, everything's made up. Okay? Everything is made up. How we graph is made up. The big difference is, do we get information out of it that might be useful? And while right now complex numbers are not incredibly useful, just algebra, they're not that useful. But if you go into more advanced mathematics, if you go into things like Calc 2 and Calc 3, differential equations, imaginary numbers start to have incredible power because they can solve expressions that were unsolvable, and you can interpret their solutions in a way that makes them fit into the real world, despite them being imaginary. So keep in mind, complex numbers are introduced here in college algebra and in Algebra 2 because they're useful later, not because they're useful by themselves. Okay? It's similar to, by itself being able to graph an equation isn't all that useful. Like, you could go your entire life and never have to graph an equation. But if you're going into certain fields, that ability to graph an equation is incredibly powerful. So keep that in mind. Anytime we talk about a complex number or a complex system, what you're doing now may not be incredibly powerful, but that doesn't mean it won't be later. Let's get started. So, it's important to note whenever we talk about complex numbers that they originated in a very specific place. In the 12th century, when algebra was being developed, quadratic equations were assumed to always have solutions. When we say solutions, what we mean is that if we take a standard quadratic equation like x squared plus 3x plus 2, and we set it equal to 0, it's assumed that there are numbers that we could plug into this and get an output of 0. So for example, in this case, if I was to use numbers like x equals -2 and x equals -1, we would get the solution of 0. If I plug in -2 squared is 4, 4 plus 3 times -2 is -6, so 4 plus -6 would be -2. -2 and +2 would make this 0. This would be a solution. If you plug in -1, same thing happens. -1 squared is 1, plus 3 times -1 is -3. 1 and -3 makes -2, plus 2 would make it 0. So these are considered to be solutions. Now, what was assumed was that quadratic equations always have solutions. And not only that, but it goes even farther, because they looked at this and said, well, that means that if quadratics do, probably polynomials do too. there are always solutions that if I take any polynomial and set it equals 0, it will have solutions. Numbers that I can plug in and get an answer of 0. Note that I'm only using this as an example of setting it equal to 0. There are, of course, other ways you can do this where you set it equal to a different number, but those are not common. Then a mathematician noticed that there was one very, very basic problem that did not have a solution, that rejected this hypothesis. Okay? This was their guess, that every quadratic, and therefore every polynomial, would have a solution. But what about this equation? Here's the thing. Mathematically, I can actually solve this equation. I can subtract 1 from both sides. I can then square root both sides to get x by itself. Common algebraic steps here. I get x equals plus or minus the square root of -1. And mathematicians looked at this and said, well, this has to be a number. And so they started investigating what numbers would multiply to -1. And they quickly found that this doesn't exist. DNE does not exist. And so unlike -2, where we could plug it in and get an answer, and -1, where I could plug it in and get an answer, this seemed to be an example that rejected this hypothesis that every quadratic has a solution. Fortunately, it does have a solution, if we just make a basic assumption. This mathematician said, well, we're going to assume that the square root of -1 is a number. Now, it's not a number that fits on the standard number line, right? We can't put it on the number line between, -2, -1, 0, 1, 2. Like, it's not in here. I just doesn't fit. There's nowhere on this number line that I appears to exist. But it is a number. It's what we call an imaginary number. And in fact, it is called the imaginary number. Now, this was just the first one. But it turned out that if we use this concept, other problems also have answers that we couldn't get before. So for example, in this case, if we go back to that original problem of x squared plus 1 equals 0, and we use I in this case, so we then plug it in with I squared plus 1 equals 0, we would then resubstitute, because remember I is equal to the square root of -1, the square root of -1 squared plus 1 equals 0. Remember, squares and square roots always cancel, meaning we get -1 plus 1 equals 0, which is true. But mathematicians quickly realized that if we have this imaginary number, we actually can solve more equations. Look at a very similar example. Let's say x squared plus 4 equals 0. Again, by traditional techniques, if I plug in a number that's on this number line, I will never get 0. If I plug in 0, 0 squared plus 4 is not 0. So 0 doesn't work. 1 doesn't work. 2 doesn't work. 3, -1, -2, -3. None of these numbers work. But again, if I plug in an imaginary number, this does work. If I sit there and say, okay, I'm going to plug in 2i. Because remember, we can always take a number and multiply it by 2 and have another number, right? 3 times 2 is 6. We didn't suddenly get pencil or graphing calculator, right? When we multiply by a number, we still get more numbers. That is just a common mathematical property. So we plug in 2i squared plus 4. We would have to distribute the squares, so they become 2 squared times I squared. Again, follow my algebraic steps here. 2 squared would be 4. I squared would be -1 plus 4. -1 times 4 would be -4. Plus 4 would be 0. And so this ends up being true, meaning that 2i is a solution to my original problem. Meaning that we once again have this hypothesis being true, because we have a quadratic equation always having a solution. This is a solution. It just doesn't fit on the number line anywhere. It's a question mark solution. It doesn't match what we currently know. Imaginary numbers always have this feel. They don't fit with our standard representation of numbers, but they're there. Believe it or not, this actually has happened multiple times throughout mathematical history. We just don't appreciate it. For example, originally, far back in like Greek times, integers were originally considered the only numbers that existed. In fact, the positive integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, they were believed to be the only real numbers. 0 was not a number. Negatives were not numbers. They didn't exist. But after mathematics took some time, they realized there's a lot missing that should be there, that we know from realistic examples should exist, right? 0 should be a number. Negatives just mean the opposites of positives. They should exist. If we can take two numbers and put them together, I should be able to take them away from each other. So addition and subtraction should exist. And here's the thing. There's entire classes taught on this concept of filling in the number line. For the longest time, people accepted the fact that only fractions existed, that there were whole numbers and fractions, and those are the only two possibilities. So -5, 4, -3, -2, -1, 0, 1, 2, 3, all those existed, and anything you could write as a fraction existed. But then they realized there are some numbers that don't fit that mold. Pi doesn't fit that mold. You can't write it as a fraction. Okay? The number e, which is a mathematical number that we'll talk about later, doesn't fit in that. A lot of scientific numbers, like the gravitational constant, Planck's constant, they don't fit into fractions. So we look at it and say, well, there must be something else that exists. Other numbers that were missing. And these are called irrational numbers. I was just the next extension forward. The big thing you have to remember for I is that I is strictly defined as being the square root of -1. If you can remember just that much, you can actually solve every problem on the post test as long as you follow other things we've done. Let's take a look. So, let's look at our first mathematical problem involving I. The big thing to note about I is always that it acts like a variable until it's squared. So, let's take a look. Where are my problems? They're there. Okay. So remember, by definition, I is simply equal to the square root of -1. At any point in time, you may use this information to simplify a problem. So, let's take a look. We'll start with talking about how to add and subtract using I. Here are two complex numbers, 3 minus 4i, added to that 2 plus 5i. These are considered to be complex numbers because they contain the real component, which is just a standard number. In this case, my real component here would be 3, my real component here would be 2, and then the -4i and the positive 5i are the imaginary components. Between these two, these are considered to be what are called complex numbers. They're complex numbers because they contain both something that is real and defined on the number line and something that is not real or defined on the number line. 4i exists, it's just 4 times the square root of -1. 5i exists, it's just 5 times the square root of -1. We just define it by those terms and then do the math. Well, in order to do this math, to add and subtract, all you have to do is just distribute the sign and then add real to real and imaginary to imaginary. So in this case, this becomes 3 plus 4i plus 2 plus 5i. We can then take the real components, the 3 and the 2, and put them together to get 5. We can take the imaginary components, put those together. -4i, positive 5i would leave a single I left behind. And this is considered to be your solution. Notice that it works the same way as if I was a variable, which is a common technique, is to think of I like you think of X. Meaning you can add I's together, you can subtract I's from each other, you can multiply, you can divide, you just think of it like an X. The only difference is, if you ever see an I squared, it's equal to -1. That's the big detail, the big crux of a lot of the problems you're going to see tonight, is that if you ever somehow end up with I squared, you need to fix that. Or actually any power of I you need to fix. So, let's continue this trend, looking at another one that we can add or subtract. So we take negative 5 plus 7i minus negative 11 plus 2i. Just like before, we take the signs to distribute them. So for this one, we'd have negative 5 plus 7i. The minus would distribute to the first term and the second term, meaning I would end up with negative and negative would make this a positive 11. Negative and positive would make this a negative 2i. And then we combine like terms. Negative 5 combines with positive 11 to give us positive 6. 7i combines with negative 2i to give us positive 5i. And this is our complex solution. So notice, we just take the real parts, the negative 5 and the 11, put them together, and the imaginary parts, just as if this was done with x, right? If this was, the original problem had been 3 minus 4x plus 2 plus 5x, right? We'd have the same basic solution. We'd have 5 plus x. It's just now we're doing it with an I instead of an x. So they end up becoming the exact same thing. You just have to remember that if you ever see an I squared, it has to be fixed. So let's look at one more real quick. Let's see, if I did something like 3 minus 4i minus 5 minus 4i. It is possible when you're dealing with imaginary numbers for the imaginaries to disappear, just like it's possible for x's to disappear if you end up combining terms that make them go away. So for example, if I was to take and distribute my negative signs, we'd have 3 minus 4i minus 5 plus 4i. I combine together the real components, which would be 3 and negative 5 to get negative 2. And the imaginary components, I end up with 0 i's, which means my solution would be negative 2. However, this is also considered to be an acceptable answer, because this one is a complex number, whereas this is not a complex number. Remember, to be complex, it has to have both parts, both real and imaginary. And so this answer is acceptable, but so is the other one. In fact, more often than not, you'll see this as the answer they'll give, because they want to make sure you remember it's with i's, whereas this one, you tend to forget the I was there the whole time. When it comes to multiplying a complex number, it actually works the same way as if you're multiplying any other number. So let's take a look. It is important to remember that when you're dealing with complex numbers, they are numbers, meaning how you solve them is done the same basic way as you would do anything else. Example, if I was to take 3 times the imaginary number 6 plus 2i, okay, this is a real number times a complex number. Well, when I multiply them, I will end up with a number that is complex. Just like with normal ones, I distribute to both parts of the parentheses. 3 times 6 would give us 18. 3 times 2 would give us 6i. Again, treat the I like an x. 3 would multiply to the 2, giving us the 6, and the I would stay an I. This works for any complex number and any product we're trying to do. Example, if I was to do 1/2 of 5 minus 4i, I would again distribute the 1/2 to both terms. 1/2 times 5 would be 5/2. 1/2 times negative 4i would be negative 2i, giving us our solutions. Again, this is how you take complex numbers and simplify them with your basic algebra techniques. Now, the more complicated version of this occurs when you multiply two complex numbers together. So again, this is multiplying a real number, like 3 is real, to a complex number. So we have 3, which is real, multiplied to the complex, 6 plus 2i. Notice that we treat it like we would treat this if this was 3 multiplied to an equation. We just distribute, right? You always have to note your distributive property. Now, if you multiply complex times complex, turns out we can borrow from some things we've already talked about. Example, if you were to take 4 plus 3i times 2 minus 5i, the way we solve this is actually by FOIL, like we did with polynomials. Think again like as if these are x's, right? 4 plus 3x, 2 minus 5x. We can simplify this by simply taking 4 times 2, 4 times negative 5, 3i times 2, 3i times negative 5i. The only big difference is that when you're finished, you're going to get an answer that's going to contain an I squared and will need to be simplified. And so make sure that when you distribute, first let's go ahead and distribute. 4 times 2 would give us 8. 4 times negative 5i would give us negative 20i. 3i times 2 would give us positive 6i. Positive 3i times negative 5i would give us negative 15i squared. Now, we are going to combine together negative 20i and positive 6i to get negative 14i. But it's important to note that we have an I squared. Remember, I squared is equivalent to negative 1. Note that this is 15 times I squared. 15 times I squared. So this would be negative 15 times negative 1. Negative 15 times negative 1 would become positive 15. So notice how the original in red becomes 8 plus 15, or 23 minus 14i. Again, everywhere there used to be an I squared, we use this property, which states that all I squareds are equivalent to negative 1. It allows us to take two complex numbers that are multiplied to become one complex number, which, again, actually makes sense. If you take two real numbers and multiply them, you get a real number as an answer. If you take two complex numbers and multiply them, you can get complex numbers as answers. Let's do another one. This is good practice to have. So again, we're going to use that property to simplify these as much as we can. So let's see. 3 minus 4i times 2 minus 5i. Here's how we're going to do this. We take FOIL, so we first, so 3 times 2, which is, of course, 6. Outer, 3 times negative 5i. 3 times negative 5 would be negative 15. I is I. Inner, negative 4 times positive 2 would be negative 8i. And then last, negative times negative would make this positive. 4 times 5 would make that 20. I times I would make this I squared. And again, everywhere there is an I, we replace with a negative 1. Again, this is 20 times I squared. This would be 20 times negative 1, meaning this becomes negative 20. We can combine these two together because they're both just i's. Negative 15i and negative 8i would become negative 23i. And the 6 would be a 6, so we get 6 minus 23i minus 20. And just like before, we can put together whole numbers together. Negative, or 20 and positive 6 would be negative 14 minus 23i. Notice that I always put my I term last. This is because algebraically, this is the common way to write complex numbers. Real comes first because it's what we're comfortable with. Imaginary comes second because it's not we're not comfortable with. So real, imaginary. But that's how you just multiply them. It's a pretty straightforward process. But do note it has to be done. Now, the last thing I'll mention is if you have an I in the denominator. If you have an I in the denominator, there is a way to get rid of it. You just have to multiply by something very specific. It's referred to as a conjugate. Let's take a look at our next problem. So, we've talked about how to add and subtract complex numbers, just like how we would add or subtract real numbers. It's just we do them in a special way. We take the reals and do their addition. We take the imaginaries and do their addition. We talked about how to multiply, and now we're going to talk about how to divide. So to multiply, you multiply it just like you would with a regular number. You use the distributive property. You multiply just like how you would do it with a complex number. You would use FOIL. To divide is what makes complex numbers different. Let's take a look. 2 plus 5i over 4 minus I. To simplify this, you're going to use something called a conjugate. To use a conjugate, you're going to multiply by the denominator, which is 4 and I. To find the conjugate, you're going to flip the sign on the imaginary term. So in this case, instead of 4 minus I, we're going to write 4 plus I. Notice how we use only the denominator. So again, for this, denominator is the important part. We're doing it all with the denominator. The top piece isn't important. The bottom piece is what's important. So, to simplify this mathematical expression, what we're going to do is we're going to use 4 plus I. This is going to cause a unique reaction. On top, we're going to have 2 plus 5i times 4 plus I. On bottom, we're going to have 4 minus I times 4 plus I. Now, this means the top and bottom are now treated like the previous part, where we simplify them by using FOIL. Let's start with the top. You'll see in a second why we multiply by this very specific fraction. This thing is super important, and you'll see why in a second. On top, we'd use FOIL. So 2 times 4 would give us 8. 2 times I would give us 2i. 5i times 4 would give us 20i. 5i times I would give us 5i squared. On bottom, 4 times 4 would give us 16. 4 times I would give us 4i. Negative I times 4 would give us negative 4i. Negative I times negative I would give us negative I squared. Now, just like before, everywhere there's an I squared, we're going to simplify, meaning we have negative times negative 1 and positive 5 times negative 1. Let's talk about the top. 2i and 20i would become 22i. Now, 5 times negative 1 would make this negative 5. Plus 8 would give us positive 3. So on top, we end up with positive 3 because 8 and negative 5, where the negative 1 is multiplied, negative 1 times 5 would be negative 5. 8 and negative 5 would give us the 3. 2 and 20 would give us the 22. On bottom, this 4 and negative 4 are going to cancel. We have 16, and you have a double negative, which means this would be plus 1, which is why the bottom becomes a 17. Notice that you are done when there is no imaginaries in the denominator. So this is an acceptable answer. You could also choose to split this into 3 over 17 plus 22 over 17i. This is the other way to write it. To write it as a complex number with a real piece, 3 over 17, and an imaginary piece, 22 over 17. Notice that to do division, all you do is do a fancy multiplication problem. But note, this piece, this one, this is the big detail that has to be done right. If you fail this piece, you fail this problem. Let's take a look at another one. I'm going to use an example here. And for this one, I'm going to use the following. We have 2 minus 3i over 4 plus 3i. Okay, again, our first big step is to use this conjugate. The conjugate is the denominator, flip the sign on the imaginary term. So here's my denominator. I take my denominator and flip the sign on the imaginary. So instead of 4 plus 3i, we use 4 minus 3i. From here, we do this like we do any algebra problem. So we'd have 2 minus 3i on top times 4 minus 3i. On bottom, we'd have 4 plus 3i times 4 minus 3i. From here, I use the distributive property, or FOIL. 2 times 4 would make this 8. 2 times negative 3i would be negative 6i. Negative 3i times 4 would be negative 12i. Negative times negative would make this positive. 3 times 3 would be 9i squared. On bottom, 4 times 4 would give us 16. 4 times negative 3i would give us negative 12i. 3i times 4 would give us positive 12i. 3i times negative 3i would give us negative 9i squared. Okay, everywhere there's an I squared, we replace with negative 1. Let's talk about on top. So this positive 9 becomes a negative 9. Positive 8 and negative 9 would make the top negative 1. Negative 6i and negative 12i would make negative 18i. On bottom, negative 1 times negative 9 would make this a positive 9. 16 and 9 would make this a 25. 12 and negative 12 would cancel, meaning the bottom is just 25. I don't like the way that's written, so I'm going to do negative 1 over 25 minus 18 over 25i, writing it as a complex number. Note that anytime you see an I squared, you're going to be replaced with negative 1. But keep in mind, this is not minus 1, okay? This is negative 1, not minus 1. Okay, don't confuse those two. I don't want to see you write a 4 here. No, this is negative 5 because 5 times negative 1 would make this negative 5. Not 4. Don't be that person. I hate that person a lot. Same down here. This 9 becomes a negative 9, not an 8. It becomes a negative 9 because 9 times negative 1 would be negative 9. And then you do all your math like you would if you were doing it with any other number or variable. You can leave it here. I prefer to write it as the complex. Be consistent. Hopefully, you guys had some practice with complex numbers in your previous algebra classes. And this was just a nice little refresher for you. Keep in mind that when we talk about these kinds of problems, this is always the case. So make sure to take note of them. And this is our last big thing for the semester, for the summer. We'll be doing graphing stuff for the next couple of days, but that will not be on your post-test. It'll just be to get you better prepared for college algebra. And you can always come back and view these videos at a later time. You're welcome to look at my channel. I post random videos over college algebra stuff starting in the fall. And I'll continue doing videos, I hope, throughout next year. And we're going to try to make this into a thing. But we'll see. Otherwise, I hope you guys have a fantastic rest of the week. Remember, it'll be due on Thursday, not Friday. And hope you guys have a great rest of the day.